I'm going to read along this question and as I spot some keywords, add them to the diagram. So we've got a small block B of mass 0.2 kilograms. That means there's going to be a weight of 0.2 g, where g is gravity and 9.8 in this case. As a consequence, there's going to be a normal reaction force from the ground, and I'm going to call that RB. Then we've got particle P of mass 0.5 kilograms. So this gives 0.5 g. And there's going to be a normal reaction force from the ground here, but it's going to be going at an angle. So I'll call this RP. And I'll also put a dashed line in for later on. Then we're told that they're attached at the ends of a light inextensible string. So this is how they're going to interact. And P is going to try and pull B to the right. So there's going to be a tension going this way. And then B is going to try and stop P from going down the slope. So there's going to be a tension acting that way. Equal in I don't say equal and opposite because they're not in the opposite direction, just they're going to have equal magnitude. Strings taught us your normal sort of assumptions that it's light and inextensible. We're told that the block can move on the horizontal surface, so it's trying to move to the right and it's rough. So there's going to be a frictional force acting this way. The inclined plane, however, is smooth, so there's going to be no friction here. So I'll label this F, let me call it FB, just to indicate it's on B. We're told that the plane makes an angle of theta. Okay, we had that before, to be honest, but I can label that as theta as well. The reason for this is if I drop further down like this and make a triangle, this is 90, then this is 90 minus theta, but this is also a right angle, the way I've defined the line to be, and therefore that's where theta comes from. Sort of get into the habit of just putting it in, but it's good to think about like why it is. It's not like an alternate angle or anything like that. Then finally, we've got that tan theta is 3/4. So away from everything, I'm just going to draw a little triangle with theta. And then O over H, 3/4. This is a 3, 4, 5 triangle. You can apply Pythagoras' theorem if you want. What it does, without a calculator, is give us sine theta, which is going to be 3/5, and cos theta, which is 4/5. Okay, it's taken a little while, but we are now set up with this question. That was all of this. I'm going to scroll down, just leave the key parts that remain, and copy my diagram across. So we're told the system is released from rest. Okay, let me scroll up. That means u is going to equal 0 for both. And in the first 0.4 seconds, that's going to be t is 0.4 of the motion. P moves 0.3 meters down the plane, so S is 0.3. So P is going to go this way, and B is going to go this way. So B is also going to move 0.3, but to the right. B does not reach the pulley. Okay, so the system's not going to change in that respect. There's going to be the same kind of suvat essentially for each of them, although they're going to be slightly separate because they're going in different directions. Find the tension in the string during the first 0.4 seconds of the motion. Well, let's take a look first of all at P. Okay, this is a connected particle system. That's why I've labeled some of the forces in red and some in blue, because we can bring it together, but we can also treat them separately. Well, actually, we have to treat them separately because they're not accelerating in the same direction. The reason I go for P first is that with B, there's more going on. There's a frictional component as well, which we don't know anything about, and part B talks about this, so we can't You could write, actually, when I did this, I jumped straight in and wrote some equations down for b's. If you do, it's okay. It's just you're then going to have to come back. So I'm just going to deal with p first. So I'm going to, we're told that we're moving, so I'm going to apply f. No, I'm not going to apply f equals ma. We've got some information on u, t, and s. I'm going to apply suvat down the plane. And that means that I've got, well, I've already got some of these things written down. So s is 0.3, u is 0, t is 0.4. And that will allow me to work out the acceleration, because then I can apply F equals ma. So s equals ut plus a half at squared. 0.3 is going to equal a half a times 0.4 squared. So a half times 0.4 squared gives me 2 over 25, and then a is going to be 0.3 divided by that. So 3.75. Okay, now I can bring that in. I'm still working with p and apply F equals ma down the slope. So this time I've just got the component of the weight acting down the slope. It's going to be 0.5 g. Now I always think, like, if I turn it into the angle, that's going to be the cos component here. So it's going to be the sine component. You've hopefully got your own way of doing it. You could draw a triangle. I see people do that. But I just think if I turn it into the angle, it's cos. Otherwise, it's sine. So it's 0.5 g sine theta minus t is going to equal 0.5 times acceleration, which I now know. Sine theta, we have the exact value, it's 3 over 5. And therefore t is going to be 0.5 g times 3 over 5 minus 0.5 times 3.75. Which gives 1.065 newtons. I'm going to round that. This is a model, so I'm going to round that to 3 significant figures. We can't write it accurately to 4. 1.07 newtons. Okay, that's that bit done. So part B then says calculate the coefficient of friction between B and the horizontal surface. So it's now all about particle B. Okay, I'm going to bring another copy of this diagram down, just because otherwise we'll lose it. But the important thing is we've got T as 1.065. Okay, so on to particle B. Well, I can first of all resolve forces in the vertical direction, and that means that RB is going to equal 0.2 g. I can now apply the friction formula. The frictional force is less than or equal to mu r, but in this case, because it's moving, FB is going to equal mu r. This is what we learn anyway in mechanics, as part of our model setup, basically. Okay, so I'm not going to go into any more detail on that, but what we are going to find is that it's going to equal 0.2 g times mu. And I'm now ready to apply F equals ma in the horizontal direction. So I've got 1.065 minus the frictional force 0.2 g mu, and that is going to equal the mass 0.2 multiplied by the acceleration, which we calculated before, as 3.75. So carefully work through this connected particles question. It's a bit like a year one question, to be fair, but you're having to contend with friction and slopes. It's the same sort of thing as when you would have looked at maybe a pulley, like a mass here, and then a pulley here. You have to sort of treat them separately. Okay, there's more going on, but basically treat them one at a time. And we can rearrange this. So that means mu is going to be 1.065 minus 0.2. Of course, you can put these things into your calculator along the way if you want, but I'm going to basically, I've rearranged it to make 0.2 g mu the subject, and then I'm going to divide by 0.2 g. Which gives 9 over 56, or 0. Let's write that to start with the exact. And it was 0.16071, which I'll round to three significant figures, 0.61.